Hi everyone, this is John. In today's video, we're going to be covering a simple Bessel function problem. So this is designed mainly to give a very brief brief example into solving Bessel function problems, and we're going to be modeling the heat distribution on a circle with respect to time. So step 0 is we're going to draw the shape. So we're given a P du dt is equal to k Laplacian u. So we're going to be on a circle. According to the boundary condition, our circle has a radius a, and on the edge of the circle, it's equal to 0. And then our PD is going to model the heat distribution over this circle, so we can think of this sort of like a metal plate, and we're trying to model its heat distribution across some infinite period of time. Okay, so now that we have drawn our shape, we can proceed with separation of variables. So let's call, since we have a triple variable dependency, we know that we're going to have two separation constants, or one or two, two. So let's call the first separation constant separation r theta, and then let's call time a function of h. So if we plug this in, what we should end up with is 1 over k, 1 over h, dh dt is equal to 1 over phi, Laplacian phi is equal to negative lambda. Okay. I chose negative lambda because we know that heat is going to decay as time approaches infinity. So we need our function in time to decay. So it would be an exponentially decaying function. So if we go down here now and we continue separating variables, let's call phi of r theta a decomposition of f of r and g of theta. And what we should end up with is, if we expand out the Laplacian and polar coordinates and plug everything in appropriately for f and r, or f and g, sorry, what we should end up with is 1 over f r d dr r df dr plus lambda r squared is equal to negative 1 over dg d squared dg d theta squared. Okay. So now we have to choose another separation constant, because we have separated the dependency for r, so the spatial on one side. Sorry, actually, let's just do this as we've put all the f of r's on one side, and then all the g of thetas on the other. So we're going to have another separation constant. And we're going to choose our separation constant mu to be a positive number. And the reason for this is, although we're not explicitly given them, we have implicit periodicity boundary conditions. Implicit periodicity. And recall that periodicity boundary conditions are basically stating that actually it should be r theta t is equal to u r negative pi t. And then the same is true at their positional derivatives. So in order for that condition to be true, we need to have sine and cosine solutions right here, such that g of theta satisfies periodicity boundary conditions. Okay. So now that we have our three diffie q's, we can go ahead and solve each of them now. Okay. Recall that we want to solve for our differential equations first. We want to solve for the differential equations such that we can get information about our eigenvalues first. So what I'm going to do is I'm going to solve the g of theta case first, because that's something that's actually given on our table. So when we solve for g of theta table, notice that it's periodicity boundary conditions. And if you pull it out from your table, g of theta is going to be equal to C1 sine m theta plus C2 cosine m theta, where mu is going to be equal to m squared, where m starts from 0, 1 onwards. Okay. So that's g of theta. Okay. Now, the f of r function is the next thing I'm going to determine. And although it is unfamiliar, this is the first introduction to the Bessel function, and the point of this video is to mainly show examples on how to solve Bessel function problems as opposed to go into their full under theoreticalness, I would say. So just bear with me. I'm mainly doing this video to help you guys be prepared for your exam. So let's first multiply everything by f of r, so that we get r dr, r df dr plus lambda r squared f is equal to f mu. So now I can pull the f mu term onto the left hand side such that we get lambda r squared minus mu is equal to 0. And I'm going to just copy and paste this down here. So what I'm going to do next is I'm going to expand this left hand side term. So if we take the product rule of everything, we should end up with r squared d squared df dr squared plus r df dr plus f lambda r squared minus mu. Okay. So what we're going to do is we're going to do a change of bases now. So our goal is to get this differential equation into what we call Bessel's differential equation. So in order to do that, we have to do a appropriate linear transformation going from here. So we're going to let z be equal to the square root of lambda r. And then if we do the various change of bases things for derivatives, what we should end up with is z squared d squared df dz squared plus plus z df dz plus f z squared minus mu. So this is a change of bases, and we're basically changing the derivatives with respect to z. Okay, remember that mu we originally found it out to be m squared, so let's plug that value in. And this differential equation right here is what we call Bessel's differential equation. And although it looks like a Cauchy-Euler problem, you can immediately tell that it's not, mainly because of this term, which causes some funky stuff to arise. But the solution to the Bessel function, well, Bessel's differential equation, are given by a linear combination of j and y. Okay, so j and y are these two things that are essentially oscillatory decaying functions. And what do they look like? Okay, so if I draw a graph of them here, so J1 sort of looks like this thing. Let's call it J1. J2 sort of looks like this. J3 sort of looks like this. You get what I'm trying to say. There you look like oscillatory decaying functions. Whereas if I draw y, so the function for y sort of looks like this boy. Let's do a different color. Let's do pink. Y2 sort of looks like this. Now, I'm drawing a bunch of stuff right now, and it's kind of looking a little convoluted, but the big point of emphasis here is that J is bounded at x equals 0. Y is unbounded at x equals 0. right? So another way of saying this is that the J Bessel function behaves at x equals 0, whereas the y function does not behave at y equals 0. The y function is not behaving at x equals 0 and rather explodes as x approaches 0. Okay. So why that is useful is, remember the concept of the singularity in polar coordinates. Remember that when we were doing circle problems, we always wanted to get rid of the case that exploded at x equals 0, or sorry, at r equals 0, because that did not obey our concept of boundedness, right? Recall that the limit of f of r as r approaches 0 must be less than infinity. So in applying this limit to our f of z function, remember that f of z, it can also be written as f of r is equal to c3jm r square root lambda, because that's how we defined it earlier. Let's make these constant c4 just to go with the flow. And we take the limit of this f of r as r approaches 0. Jm is bounded as r approaches 0, okay? So Jm bounded. However, Ym explodes. So therefore, we need to let C4 be equal to 0 in order to satisfy the boundedness condition. So let me just write that down. So now that C4 is equal to 0, our f of r function is going to look like C3jm r square root lambda. So the ym term has been effectively eliminated, because as x approaches 0, or as r approaches 0 in this problem, ym explodes, but jm does not. Okay. Now, a quick thing to make sure you guys understand this, right, is if we were doing this problem outside the circle, we would keep both the jm and ym term, because we do not contain the singularity anymore. If we were doing an annulus too, so an annulus problem, remember that the annulus does not contain the center of the circle. The annulus does not contain that. Does not contain center. So therefore, we cannot eliminate terms via boundedness. Okay, cool. So this is our f of r function. But recall that we have another boundary condition that we can use to actually find the value of lambda. So recall that we have this boundary condition u of a theta t is equal to 0. So in plugging that in, so f of a is equal to 0 is equal to c3jm a of square root lambda. We're effectively trying to find the zeros of the J Bessel function. So I'm going to draw a fresh graph of the Bessel function for Jm, and let's just do some random Jm. So let's just say Jm. Notice that Jm has various zeros, right? So this could be the first zero of Jm, where I'm going to denote it by z, z1, the second zero of Jm, z2, third zero, j3, fourth zero, j4, fifth zero, j5, on to z, n. So the point of emphasis here is that the zeros of this Bessel function are separated by some arbitrary interval, right? They're not separated by the same exact periodicity as compared to, for example, a sine function, right? If we were to draw a sine function here, we know that each of the zeros are separated by a certain interval, right? So this is going to be pi, 2 pi, 3 pi, on to m pi, whereas there's no distinct periodicity or repeating pattern for the zeros of the Bessel function Jm. So we call z, we're going to call zn Zn is the nth zero of the Jm Bessel function. We should probably put an m here, because the zeros of the Bessel function are dependent on whichever Jm you use. So each of the Bessel function has different set of zeros. So what I'm saying is that for example, for the first Bessel function, so z1 of n, that would mean the zeros of the first Bessel function, or the J1 Bessel function. Okay. So going with that trend, we don't want C3 to be equal to a constant 0, right? So that non-zero. So therefore we're looking for the zeros of Jm. And the zeros of Jm can be modeled in the exact way I was just talking about. So the zeros of Jm are going to be equal to Zmn, where Zmn is representative of the nth zero of the nth zero of the mth Bessel function. So the mth Bessel function determines the zeros. So therefore lambda mn is equal to Zmn over a squared. And this iterator would start from n equals 1, because the first zero of the Bessel function is going to be called the first zero, not the 0th zero. So if we started from n equals 0, we would be calling z the 0th zero of the Bessel function, but that doesn't make sense if you say it like that. Okay, great. So now that we have everything, we can essentially just plug everything together now. So recall general solution. So now we have u of r theta t is a decomposition of phi r theta h of t, which is equal to f of r g of theta h of t. So plugging everything in, u of r theta. So notice that we have two separation variables, so we have to make sure we start everything at the appropriate interval. So in this specific problem, we can start our summation from m equals 0, and we don't really need to isolate anything, because j0, so j subscript 0 is the same thing as everything else. Hopefully you guys will see what I'm saying in a moment. So j of m z mn r double bracket a mn sine m theta b mn cosine m theta, and then the solution for the h of t, which I don't think I wrote up there, but can be easily found, which is just negative mn kt. So this notation is basically just saying that I'm multiplying this term by this term and then this term, and then the second term would just be this times this times this, right? So it's essentially just matrix multiplication. A more simplified way of writing longer solutions for MATH-241. Okay, so going with what I was just saying, although I usually emphasize taking out 0, for this specific problem, it doesn't really matter, because for each of the m equals 0, for the m equals 0 case in this particular problem, it doesn't generate any sort of different solutions, so we're able to write it in as one full summation as opposed to two separate ones. Okay. So now solve coefficients. Recall that we were given a initial condition of this form. So in applying that initial condition now, we will have to solve for both amn and bmn, seeing that f of r theta is just an arbitrary initial condition. So let's apply that. 0 is equal to f r theta is equal to everything here except for the last term, because that just becomes 1 at time equals 0. And then if we solve for a of amn, so we're gonna have to use double orthogonality here. So notice that we're going to have to take the integral with respect to theta and r. So in theta, we're going from 0 to 2 pi, or you could also do negative pi to pi. Just make sure you get the full circle. 0 to 2 theta, and then 0 to a, so the full length of the circle. And we're going to have to do orthogonality against the Bessel function. Sine squared and theta squared, and remember that we're in polar coordinates, so we have to do r dr d theta. And then on the top, a 2 pi f of r theta sine m theta j m lambda mn r dr d theta. And the coefficient for bmn will look very, very similar to this, except it'll have cosine terms here. So hopefully this clears up some preliminary confusion on Bessel functions and how to solve them. This video is mainly intended to give you guys a brief introduction onto them to the extent of your second midterm. Yeah, hopefully that helps, and please let me know if you have any questions on the piazza. Have a good day.